Hello, everyone. Thank you so much for taking time out of your day to join us for today's webinar. Today, we're going to be talking about machine learning and giving a great introduction. This is the first of 6 in our data science series that will occur every other month. If you have any questions throughout the presentation, feel free to utilize Zoom's Q&A tool on the navigation bar. We'll address the questions at the end. Today's moderator is Tom Marlow. Tom is the Chief Technology Officer at Black Hills IP. He's going to be presenting with Dr. Manjeet Rege. Dr. Manjeet is the Director of Center of Applied AI at the University of St. Thomas, and he is a wonderful advisor here at Black Hills IP. I'll hand it off to you, Tom.
All right, thanks, Justin. So like Justin said, I'm Tom with Black Hills IP. I'm a patent attorney, and Black Hills is a legal tech company. And as the title mentioned, this is a webinar series about data science and artificial intelligence. Now, without a doubt, those are very cool and interesting topics, but why are they being sponsored by a IP legal tech company? So here's the deal. Most industries these days are being impacted by the advances being made in computational intelligence and data availability. And really, the legal field, it's no exception. Unfortunately, for many, these technologies and processes can just be a black box, kind of like an incomprehensible mess of words and numbers, with the customer just being expected to accept that the results are somehow better. We here at Black Hills have fully embraced the value of technology to assist our people and empower our customers, whether it be from big data tools, complex expert systems, process automation, and artificial intelligence. We tackle all of that, and it's really in the DNA of what we do and what we bring to the market. So it's important to us that what we do is not just a black box. These technologies, they're the future for this industry, and we want you all to be there with us in this. So now, thankfully for me, as Justin mentioned, I'm joined by Dr. Manjeet Rege, a renowned expert in data science and AI technology. Manjeet, glad to have you here. I'm really excited about this series, and thank you for doing the heavy lifting.
Sure. Thank you so much, Tom, and thank you everyone for joining us. As we heard, this is a first in a number of other webinars that we are having this year, focused on different aspects of data science. AI will be our next one. And today we'll get into what is machine learning. But before we talk about what is machine learning, let's first talk about the importance of machine learning, why machine learning is suddenly so important everywhere. If you look at the quotes, coming out from many of the industry leaders in the Silicon Valley, you will hear that a number of companies are moving towards what we call an AI-first enterprise. Google primarily started its journey as a search-first company. Then they redefined themselves as a mobile-first, and now to an AI-first. And like this other quote as well, machine learning is the next transformation. So there is a lot of buzz around machine learning these days. If you look at the gadgets around you, almost every piece of software that you make use of, you have machine learning embedded in it. That is why I often say that the field of software engineering has changed from a traditional software engineering to engineering intelligent software. If you look at a number of products or services that we make use of, whether it is uh, the pictures in the cloud that get backed up whenever you take a picture, those pictures are nicely organized for you. Um, so you have a cluster of pictures of you, your spouse, your friends. There's a machine learning algorithm that is doing that behind the scenes. In your Gmail inbox, based on the content, you are shown 3 different responses for you to select. So that will, when you select that, it will automatically pre-populate your response. So one is a negative response, one is a positive, and one is a neutral. So that is analyzing your text coming in, and it is preparing a text for you to send out. Self-driving cars, once again, the same thing. Spam detection in your inbox. Recommendation systems has been the most, I would say, revenue generating application of machine learning out there. If you think about how our lives have changed with recommendation systems, be it on an Amazon app, it tells you what to buy. On LinkedIn, a recommendation system is telling you what jobs to apply to. On Facebook, it will tell you who to be friends with. On Yelp, it will tell you what restaurant to go to have lunch, for example. So instead of you going and looking for items, we are presented with a wide array of items to choose from. So in terms of why machine learning, I'm sure you must have seen examples like these where we are generating more data than before, and then many of these large Silicon Valley giants processing so many or so much data on a daily basis, either generating or processing. So what has that got to do with machine learning? Fine, we are producing large amounts of data on a regular basis. Well, data is the raw material for machine learning. It is the fodder that is getting fed into a machine learning algorithm. Now, we are generating more data than ever before. Now, we're also storing a lot of data because the cost of storing data has gone down significantly over the years. So if you look at this table, this is the cost of storing 1 GB of data over the years. So 1 GB, I mean, we all have USB drives or pen drives that are easily 20, 40, 60 gigabytes these days, and we can buy them for about 30, 40 bucks. But the cost of 1 GB, if you look back in history, was extremely high. So if it is not costing you, then the obvious tendency from an enterprise perspective is to gather and collect more and more data. And of course, the hope is that more we collect, perhaps we end up doing better in terms of knowledge discovery, or whether in terms of our predictive ability. As an example here is an experiment that was done by researchers in 2001, right about the time when this wave of big data had started with the evolution of World Wide Web. And what this particular experiment showed was, as you collect more data, how does it help in building larger machine learning models? So if you look at these three lines, each line here in this plot is a separate machine learning model that was built. On the x-axis, as you go from left to right, that was the amount of data that was made available to the machine learning model to learn from, right? On the y-axis is the predictive ability, the model accuracy for each of these models that we are looking at. Now, what we can derive from this is that as you go from left to right on the x-axis, which means as you provide more and more data to a machine learning algorithm, the accuracy of the model goes up. That is the first. Second thing you can derive from this is that if you look at these three models in particular, as you provide more and more data, the performance of those three models tends to be similar to each other. So it's not as if one is significantly outperforming the other. Those three are more or less similar to each other. So, a lot of times there is emphasis on this new, latest, cutting edge machine learning algorithm to use, as opposed to focusing more on quantity and quality of data. So these days we talk something about a data-centric approach in machine learning. Essentially, what we are saying is there's only so much you can do with a machine learning algorithm. The real recipe to success is having larger amounts and quality of data. So when you gather large amounts of data, obviously we'll be drowning in data, and perhaps we need automated solutions for deriving information from that data. And that is where machine learning ends up playing a role. So here are a few successful applications of machine learning in different industry verticals. In the next couple of months, we all will be filing our taxes. So IRS uses machine learning to improve customer service by analyzing the incoming requests for help and information. The IRS hopes to schedule its workforce to provide faster and more accurate answers to questions, right? So demand forecasting, and then accordingly hiring more people to meet that demand. You might have seen Minority Report movie, Tom Cruise movie years ago. There, they were predicting if somebody might commit a crime. This is not about that. What this is about is intelligent allocation of resources for crime prevention. First tried out, I believe it was in Santa Cruz, California. The way they used to deploy officers at night for patrolling was that they used to just divide the city into different blocks and assign different city blocks to different officers for patrolling at night. What they decided was, what if we adopt a more data-driven approach? So we have data from the past many years. Can we perhaps predict that there is a higher probability of a crime happening in one particular region? And then if there is a higher probability, let's assign more officers there for patrolling. So that worked out pretty well in that particular city. And then many other cities, I think Philadelphia, Atlanta, Chicago, tried something similar as well. Retail banking is a highly competitive business. So let's say you have a checking account at a bank and you receive a flyer in the mail that um, we would like to offer you a home equity line of credit, or perhaps a reduced cost for your house closing, home mortgage. Now, let's say you are not at that stage in life where you're looking for purchasing a house. What you feel as a customer is that just because I have a checking account, the bank is maybe misusing my information for cross-selling other products to me. On the other hand, if I happen to be at that stage in life where I'm actually looking to buy a house, and if I receive that particular promotional stuff in the mail, I find it very useful, right? So when you target market, you have reduced cost, and you do not have your customers getting turned off because you're only approaching those that might find that particular promotion more relevant, and you're not going after everybody. So those are a few applications. We have talked about why ML. Now let's talk about what is machine learning. And often you hear the two terms AI and ML being used interchangeably. There is some difference, and in fact, our next episode is going to be on AI specifically. But let me put it this way. One interpretation of the difference between AI and ML that I heard that I like is, one way to think about AI is like a discipline, like sort of like physics. So, AI has to do with theory and methods, and theory and methods to build machines that think and act like humans, right? So that's a very broad field. Machine learning is a subset of that larger field called AI. So machine learning is a subset of that larger field that essentially provides a number of tool sets. So if I think about AI like a discipline like physics, then machine learning would be kind of like Newton's laws of mechanics. And just like you can use Newton's laws to figure out, if I throw a particular thing from my table over here, how long will it take for it to reach the ground, for example. Similarly, you can use machine learning to solve certain kinds of AI problems. Now, when can you use AI, and what kind of problems can machine learning be applied to? So let's first talk about when machine learning can be a right solution. If you already partially solve the problem using certain heuristics, certain rules, then machine learning can help you automate that. For example, let's say credit risk approval. You might have a human looking at somebody's credit history, following certain rules, and then making a judgment, either a yes or a no. So that is something that I can probably use machine learning for. Second is you have the data. Remember, I said before that data is kind of like the raw material that is essential, that is needed. And it is important that that data is clean, it is well structured as well. So if I do not have the data, so again, going back to this credit risk approval, I should have data from the past of people we have approved, people we have not approved. That becomes the raw material for my machine learning algorithm. If I do not have data from the past, that becomes a challenge. So if I have data and if I have structured rules, machine learning can be a right solution. Now, when can it not be a right solution? Let's say you have tasks that are perhaps not well defined. So for example, writing sales emails, or maybe providing support in a tech support, for example. You have to give a different reply to every support query that comes in. So you have more of an unstructured definition to that particular task. Also, if you do not have data, or you expect to collect more data in the future, which means it's not something that I can directly use machine learning on right away. I have a few examples, and I think that will kind of help in driving the point home as well about how machine learning works. Let's say I have to perform activity recognition. So what I can do, perhaps if I think about it from a programming perspective, is I would say, send me the data coming into the accelerometer of the phone of the user. And I can probably write a condition like this, that if the speed is less than 4, that is getting measured, then the activity that we are recognizing is walking. Now I'm told, how about also accounting for running? So I can change my condition a little bit and say that if the speed is less than 4, it is walking. If not, it would be running. Now I'm told, how about you also account for biking? And I further change my conditional logic a little bit more. But what if I have to recognize people, let's say, golfing? Now I cannot further append my conditional logic here anymore. But the way a machine learning algorithm would work is that you would give it data along with label. And this is something that I'll come back to again. So you would say, perhaps if you want to recognize activity, how about we convert this into a image recognition problem? So you give me an image of a person and you tell the algorithm, here is an example of somebody walking, an example of somebody running, example of somebody biking. And the algorithm looks at these examples coming in and then automatically figures out rules. You do not have to write down the rules yourself. So what is different is that in without machine learning, in a traditional software engineering, you typically sit down and write the rules like the way I showed you on the earlier slide. As opposed to with machine learning, you are providing examples and you are letting an algorithm derive the rules. So traditionally, I would provide an input and I would say that whenever somebody's credit score is in this range, the answer is no, or perhaps the answer is yes. for that credit risk approval. Now I'm saying here is somebody who had applied for our credit card in the past and we had approved that person. Here is somebody else and we had not approved. Somebody else we had approved. So you have all of these examples. Let's give it to a machine learning algorithm, and that algorithm will produce a model which is now ready for performing prediction. So another example here, each of these digits 7, right? We can easily recognize these are handwritten digits, right? So each is a separate image. And you can see that there are a number of variations in how humans write. Now, if I have to sit and write my own rules about recognizing each one of them as a 7, it would be extremely difficult because I would have to sit and come up with rules, something like whenever there is a horizontal line over here, and then you'll have a vertical line, and that vertical line may not always be straight, it might be at an angle. Sometimes you have this dash over here. You cannot cover all possibilities. On the other hand, with a machine learning approach, you can take that image, so that's your input, and you pair it with what the expected target or the label for it is 7. You give it the next image and you provide the expected label, which is 7, for each one of these to the machine learning algorithm, and it now begins to differentiate between a 7 and a 3 and a 4. So it is learning automatically based on a mathematical machine learning algorithm. You are not coming up with the rules. So going a little bit deeper further into what is ML. ML primarily could be divided into 2 branches. One is called supervised learning, which we also refer to as predictive modeling. So whenever you hear a task that involves performing some prediction, that falls under supervised learning. And then there's another branch where there is no prediction happening, but it's more into, let's look at the data and perhaps derive some patterns in it, and that falls under pattern discovery. Let's jump in a little bit into what supervised learning is. So in supervised learning, you're going from data to prediction. So a few minutes ago, I said that you provide examples of input and output to a machine learning algorithm. So in this case, you have data about whether it is sunny, what is the wind, the weekday, and the price of the electricity. So you're predicting a numeric number. Similarly, you're providing examples of a number of chest x-rays, and for every x-ray, you're saying you're providing the likelihood of COVID-19. You are giving an example of a text and an email that has arrived, and you're saying to the machine learning algorithm, this one is a spam. This next email is not a spam. So when the machine learning algorithm looks at each of these examples, each of these would be a separate machine learning model, but it now learns that whenever a new example arrives, the model is now in a position to give you the electricity price. Whenever a new X-ray arrives, it is now in a position to tell you the likelihood of COVID-19. So This is happening because you provided lots of examples, and now the model is ready to perform the prediction for you. So when the model learning happens, you are giving it data for the model to train. And for every example, you are providing what the label is. What we mean by a label is this person applied and you had approved that person for the credit risk, whatever credit card application. This other person applied, we had not approved the loan. So you have these paired examples, and over a period of time, you have a predictive model getting learned. Here is a visual example of something similar. So once again, going back to this credit risk example, you have people you have approved in the past and people who you have not approved in the past. And that becomes your data that you're feeding to the model. So for every example, you're telling the machine learning algorithm that here is a previous applicant, and for that particular application for the credit card, we had approved, and this one we had not approved. So when the model learns, it learns to go from that raw data to a model where it is now able to distinguish between when to approve and when to not approve. So when I have something like this created, you have a new loan applicant, I'll take that loan applicant, send it down this model, and if that person reaches here, we approve. Person reaches here, we deny the application. Slightly more concrete here. How does this look at the data level? Let's say you have data like this. So every row is a customer and columns are measuring features. And then you have this column that is marital status. So you decide to build a model that is going to learn to predict if the person is married or not. So to do that, once again, I need a number of examples where every example I have the label provided that this person is single, this person is married, and I have many such rows. You now give this, so this is my input, this is my output, expected output, to a machine learning algorithm, and the machine learning algorithm looks at all of these examples one at a time closely, and eventually it is now ready to make a prediction. So when we say it is now ready to make a prediction, how do we trust the model? So we'll say, okay, now that the model is ready, let's take a row of our data, give it to a model and see whether it is in the position to make a prediction. And let's compare with the actual answers that we have. And turns out it is in fact making the right prediction. So now you get a good idea about the fact that this model is capable of predicting the right answer, and perhaps this could be deployed. So what you are predicting could be categorical, like single, married, or it could even be numeric. So in this particular case, the model is predicting the price of the house based on a number of features, but in this case, only one feature, that is the area of the house. So if you go to Zillow, Zillow has a price for your house. There are also other services out there like Open Door, for example. You put in your address and it will tell you the price at which they might want to buy your house. So taking in information about the house, what you're predicting is not whether it will sell or not sell. It is predicting a numeric value at how much would it sell for. So these examples that you see, these are the past houses, the houses that have already been sold. So a house like that at that particular square feet has been sold at that price. So if you have to build a model based on this, this could be one model. This could be another model. And this could be a third model. So clearly you want a model that is learning the trend from the data. And at the same time, it is not really memorizing the past too much. So for example, if you look at this particular house, this particular model, you see that it is not learning anything from data. The pattern is this way, but the model is not capable of learning or has not learned anything. Model 2, I see that it has done a decent job in capturing the trend of the data, that initially as the square feet goes up, the price goes up, and then it begins to plateau out. And if you look at the third one, it is fitting itself very, very closely. So it is going towards perfection so much that, you know, sometimes the buyer might have paid a higher price than they should have, and sometimes the seller might have accepted a lower price. So these are outliers, and I don't want my model to take every instance of data extremely seriously. I wanted to learn a pattern, but not go towards perfection. So model 3 is going towards perfection. So model 1 is completely under-prepared, model 3 is over-prepared, and model 2 is optimally prepared, what we call an optimally fit model. So I spoke about supervised learning and about prediction, and that prediction could be numeric, like that house price prediction, insurance premiums predictions, or it could be categorical, like should we be approving somebody's application or not. Now, the other branch of machine learning is what we call unsupervised learning. In unsupervised learning, you do not have a outcome to predict, but you might want to do certain clustering or grouping of your data for a number of tasks. So you might have heard about market segmentation or customer segmentation. So you have your consumer data, and what you perhaps want to do is group your consumers into different groups. Why would you do that? Well, let's say I have a retail store, and I have people coming to my store from age 15 to 85. From a marketing perspective, I do not want to approach all of them in a similar manner, Maybe for senior citizens, I might send them mail in letters. For youngsters, maybe I might approach them through social media or something like that. So if I take my consumer base, I can group them into different groups. Here is another example. So I have a lot of customers, and here we have looked at age and income and come up with these groups or clusters. So when you perform these clusters, you realize that here is a group of my customers, higher age, lower income. So probably they are retirees, or lower age, lower income, probably they might be students. And then you might have a customized strategy for reaching each one of them, as opposed to having a one size fit all approach when you're reaching your consumer base. If you look at a news aggregator like BuzzFeed or Google News, the so you see the main story, and then below that you see a cluster of other news outlets that are running a similar story. So this is another example of clustering, because news articles have similar word usage and other features like sentiment, topic analysis. And based on that, you could derive other news articles that are dealing with the same topic. So this is not happening in a supervised manner. It is happening in an unsupervised manner. Let me talk about a few things about machine learning in the real world. So a common misconception is that one machine learning model can do it all. And it takes certain skill, certain experience in breaking up a particular business task into multiple machine learning models. For example, if you want to predict whether a product will go out of stock or not, you may have one model that is predicting demand at that particular location. So the data that it takes into consideration is going to be different for these other models. So this is perhaps looking at the seasonality effect, the weather, whether there's a big event happening, things like that. And based on that, predicting a demand at that location. Now, if there is a high demand, my second model is looking at predicting inventory at the warehouse and nearby stores. So that's a separate model derived based on a separate data set collected. And the third model is predicting how long it will take to restock if you end up having a high demand and if you go out of stock in that particular place. So if it is something quick, then I'm not going to be going out of stock. But if it takes a long time, then maybe I might be going out of stock at that particular location. So you're breaking up a particular question into multiple machine learning models. Here is another example. You might have used Google Translate app. Behind the scenes, it is dividing that task into a number of models, and each one is specialized to do a separate task every time. So model one just identifies where the sign is that you're looking at, right? So you're pointing this phone to this particular sign over here. So somebody might point it from this side, somebody might point it from this side. So sometimes that sign could be at the top, at the bottom, at the right. Model 1 just eliminates all that noise, cuts out everything else, and just gives us the sign. Model 2 is detecting what the language that you're pointing to is. So again, that's a separate data set that whenever I point out something to you, the output has to be one of these existing category of languages. Model 3, so now that you know the language, model 3 would actually read it, and model 4 will now look at, if this is the language that we detected, what is the translation of that? So there will be a separate model that does that behind the scenes. So the entire knowledge discovery process flow where machine learning is utilized, it's an extensive exercise. You first start off with understanding the business process that you're perhaps trying to automate, followed by understanding of the data behind it. If you directly just look at the data, you might not realize the overall business process. A lot of the data is not collected with the goal of applying machine learning. So data preparation, data cleaning often takes about 70 to 80% of this entire cycle. Once you have the data in a particular format that you want, you are now ready to build a model. This takes the least amount of time. The model that you have built, you need to evaluate that. Remember that house prediction example, I said some models could be over prepared, some of them could be under prepared. That is what this evaluation step is. And once we are happy, you deploy it in production. And when you deploy it in production, there could be certain surprises. You might notice that the data that is now getting served to the model is different from what we were given when the model was trained. So you need to continuously monitor the performance of the model once it is deployed. A model is only as good as the data it was trained on. And if that data is perhaps obsolete, stale, or out of sync with the production data, then it's something we need to take care of right away. Now, sometimes in the real world, you often see machine learning models not going from a proof of concept to actual production. You see a number of proof of concept models getting built within like a very short span of time, like a couple of weeks. But after that, they have a quick death. Either a lot of them do not make it, or very few of them eventually make it. So there is a reason behind that. That there are three parts to a complete machine learning solution. You have the data, you have the code, and then you have the model. So when you build a proof of concept, your data typically is a sample that you have extracted from your large data set. You have perhaps spent some time cleaning it, and you have built a proof of concept. When you put the model into production, a number of things may happen. First of all, that data might get scaled up. Second is you may not have static data coming at you. You might have live streaming data being presented. Third, you may have what we call concept drift or data drift. That is, the data you were given to build the model was fine when it was given to you, but now that we have implemented the model and put it into production, the data now coming is perhaps a little bit different. Think about in a number of financial applications, they noticed that people's behavior changed during the pandemic. There is a lot of online purchasing going on. So before the pandemic, if I trained the model, I would have flagged that as unusual. But taking into consideration what is happening in the world, my model has to be able to handle that. Code. Again, when you write your initial proof of concept, it is a few lines of code, but putting it into production, there are a number of software engineering pieces that come into play. And I'll shortly show you a picture of that as well. So here you have your basic simple code that took in the data and it worked out fine, but you're not showing code. You're not showing machine learning Python code to an end user. You have a number of other peripheral things like a nice app which makes it easier to use. And that is a lot of burden. So that is a lot of code that has to follow certain software engineering best practices. Finally, the model itself. The model, while training or while developing the proof of concept, might have been running in your memory, but now that you're serving live audience or data, it needs to scale up as well. And every time I make a change, I need to probably keep a track of different versions of my model as well. Many times you make a change and you notice that your model is not working anymore. So I should quickly be able to go back to the earlier version. I spoke about the fact that when you go from a proof of concept to production, your code base increases. So in this particular picture, you see that the actual machine learning code is a very small part of the entire machine learning system that has been put into production. So this could probably be around 5% or maybe 10%, but you have these other moving parts of the entire machine learning pipeline. And that is where you need to have a good team that is able to handle these other pieces. For developing a proof of concept, one person might do it, but you need the right team for managing these other moving parts as well. So when you're building a team, having the right skill set is extremely important as well. And here, we have these two scenarios. One approach is to hire a PhD in, let's say, machine learning, and you have a bunch of these PhDs working together. As I showed you before in that result of machine learning algorithms and big data, it is not the newest cutting edge algorithm that makes the difference. It is the data that makes the difference. So machine learning PhDs typically are fine-tuned for developing a new solution, whereas a software engineering team is fine-tuned for utilizing perhaps a pre-trained machine learning model developed by some other company and freely available. So you don't have to train, or you don't have to come up with a new algorithm. You need to make use of existing models out there and adapt that to your data. It is your data that makes the difference, not the newest algorithm that was published 2 days ago. You often see big companies like Google and Facebook, they happily open source their algorithms, right? They give access to their models, but not to their data. It is the data that differentiates and helps you have a competitive advantage. So it helps to have, yes, maybe a few PhDs, but software engineers who are able to nicely come up with these other building blocks and have them work together, as opposed to just a PhD focus on building newer algorithms. And then constant reskilling is extremely important as well. So I'm almost out of time, so I'll stop here and hand it over to Tom.
All right. Thanks, Manjeet. That was a great intro session on machine learning. And I'm taking a look. If you have any questions, now is the time to post them. There's a Q&A button down at the bottom of your screen. I'm taking a look and see what we have. All right.
So there is a question on chips, packages.
Yeah.
Yeah, so I can take that.
Great.
So in terms of compute, right? So there is, of course, CPUs, and CPUs have a limit. Now, GPUs, that is the graphics processing unit, have been shown to be extremely useful for matrix operations. And a number of models use GPU. Now, Google also has something called TPU, which is a tensor processing unit. And if you're using Google's ecosystem, TPU, and if you have large amounts of data, then TPU is the way to go. So a number of these cloud providers allow you to make use of GPUs at a very reduced cost instead of investing and buying any of this.
In fact, I think even with the free version of Google Colab,
right,
you can get access to GPUs and maybe even a
TPU.
TPU.
Yes, exactly.
Yeah,
you have to be careful
free.
with that, though. you get kicked out sometimes. Yeah.
But there is at least it's good to know that there's some accessibility for those for early stages of testing things.
Absolutely.
There's another question here that is maybe I'll be able to cover from a patent perspective. What aspects of machine learning are patentable? This is a topic that is really hot right now in the IP community, especially with the past many years of debate on the patentability of software in general, because a lot of what we're talking about with machine learning is, well, software based. So the way, and of course, it's going to vary a little bit country by country, but the way things are tending to shake out now is that the key with being is that there are aspects of machine learning, artificial intelligence technologies that are developed that are patentable, including applications of these technologies. The key is when looking at the technology that you are trying to protect, is there something in it that has a technical feature outside of just being run on a computer, or outside of just the high level of saying using machine learning or using some sort of artificial intelligence algorithm to do it, that is not yet known or not yet obvious. And I know the obvious piece is a lot grayer than the first, but the idea is there some sort of a technical component or technical application that that isn't out in the public already, that using machine learning now becomes something new? Let's see. Oh, there's a follow-on to that. What are some of the big pitfalls in writing machine learning applications? Well, I think the biggest one would be trying to define something that's already known, some sort of say some process, and focus on just doing it generically using machine learning. You're not going to get something like that allowed. You've got to focus on the new technical aspects, whether that be in how the data is collected, some novel way of doing that, or some novel way of treating the data, which to what Manjeet was talking about, a big portion of what makes machine learning successful is the type and quality of data going in. So if there's things that can be done to process and massage the data to make it more reliable for doing machine learning, possibly some potential there.
And then we have one question. What will be the next transformation? After all, you have discussed mobile first to AI first too. Yeah, so if you look at the impact of AI in recent times, there has been a big impact on unstructured data, right? Like images, for example, natural language processing, which has allowed us to deploy some of these models on devices. So this new term that is getting coined is artificial intelligence of things. So where you would have edge intelligence. So the model that you have learned, the knowledge that you have learned, you're deploying that on a number of edge devices. It could be in manufacturing, for example. Every time you notice something is, let's say, not manufactured correctly, I do not want to contact the server, but perhaps have that camera there make a decision very, very quickly there. Are there key developments in GPU packaging to increase their performance to deal with AI and ML specific applications? So NVIDIA typically does that, right? They come up with a lot of advancement in terms of what they offer. But the good thing for us consumers is that you can access all of that through the cloud. So you would not be investing in buying the GPU yourself.
Let's see. We've got, given that the magic lies in the data, to what extent does the ML model itself have to be described in a patent application? Well, again, that's going to depend on what it is exactly that you're trying to protect. Now, if it is the model itself that you're trying to protect, obviously that is going to have to be described, and then you start questioning kind of the balance between disclosing it in a patent versus trade secret. And I think a model can be a great candidate kind of for that discussion around should it be protected with trade secret versus patent, just because of how kind of black box they can be. And if you put it into a patent application, then the big question is, should you need to enforce it? Will you be able to tell if a competitor is using your model? So I think that's probably the biggest piece to consider when looking at that.
All right, are we good?
Yeah, thanks everybody for all these questions. We might not have been able to get to all of them because we're running over time. Please continue to bring these questions and interests to the upcoming sessions. Like Justin mentioned at the start, we're going to be holding these every other month through the year. And I guess the takeaway that I would give for everybody from here interested in this and interested in kind of the learning that we're going to be doing over the course of the year is think about the processes that you encounter day to day at work, and some of those things that require a decision to be made, what data or what input is needed to make those decisions, where are there patterns that can drive some of these decisions. And then where do you currently have records? Where do you currently have data that could be leveraged? Consider like categorization applications, places where predictions may be useful. These are good places to start in your work or practice, looking for opportunities to leverage some of this technology. Of course, we here at Black Hills IP are always available to talk and work with you on getting the benefits of this technology into your organization or firm. Feel free to reach out. So we're going to leave you with that for today. Thanks everybody for joining, and look forward to discussing these technologies over the course of the next several months. Thanks.